Let's take a 5-minute, a little mental chill out, because we're going to change topics. And the CTE told me that we got to stop every few minutes. And I said, do demos count? And they said, yes. So like, well, thank God. Because I'm not stopping for any other reason. But now we're just stopping for fun. Or we could keep going and finish early. Let's see. CTE hasn't studied that. Let's see. All right. So the last thing we're going to talk about for energy is energy diagrams. Because this is the one thing that you might actually need in your life here as we go forward. So let's look at, this is like a general thing that is used in a lot of fields. So let's look at one. Energy diagram, important tool for, I would say, visualizing, but you can actually get math out of them, which you'll do on the homework, for visualizing interactions. Mostly like molecular kind of interactions. Okay? So let's see. Oh no. Let's see. Oh, is the third scenario, what is happening? This isn't clear. Oh, this is like the cannon shooting the cannonball, like a trajectory. And at the top of the trajectory, it hits another cannonball. Oh, these are different cannonballs. Here you go. That's never happened to you? 2 cannonballs on a hill? Okay, so visualize. So first, let's get an interaction going here. Oh, yes. How about one of these? A mass and a spring moving along an axis starting at 0 at the natural length. So there it's just a happy mass and a spring like that, like this, except this one's upright. We can pretend there's no gravity. Okay, right, so we can move it up and down. So right now it's at rest. Net force is 0 because this little bit of a stretch we get cancels gravity. So pretend there's no gravity and this is the natural length, and we're all like, what? Right, so that's what it's like. Okay. So now what we're going to do, all we got to do an energy diagram is plot the spring potential energy. We can do that, right? As a function of position. So here we're going to say x is up. I can't do it sideways because I have to get an air track and it's very loud. Right? So I pull down, the potential energy increases. And if I push up, the potential energy increases. Right? Either way you go, if you pull down, you put in energy because the spring wants to pull it back because you extended the spring. If you push up, you put in energy because the spring wants to push it down. Because remember, what was the equation for US? It was 1/2 kx squared. Remember, the spring kinetic potential energy was 1/2 kx squared. So all we're really asking you to do is plot 1/2 kx squared. So I can do that. X squared looks like this. Like that. You can even make the noise. Oh, it's not very good. Well, it's good enough. You can make the noise. You can make the chalk make the noise. Potential energy diagram. There it is. What was I going to do with this? Okay, oh yeah. Now, imagine a mass moving on a spring at some energy. Hey, these notes are useful. I should just use these sometime. Now imagine a mass moving on a spring at some energy. How to represent this? All right, so now the mass, now we're going to make it move. Moving, right? Back and forth. So you would say, well, you got to think about the turning points, really. So in an oscillator, we'll talk about oscillators more at the end, but it's really the turning points are the interesting part. Right? The turning points is when it stops. It's moving up and down, and the lowest it goes right now. Right here. Right here. And then up at the top. Those are turning points. So turning points, it's not moving, so it has no kinetic energy. Turning points, we could say V equals 0, so therefore K equals 0. So that's when it's going to be at its maximum kinetic energy. That's also for the spring when it's at its maximum displacement. So you could say this is probably a turning point right here. Right? So the thing moves out to x, and then it becomes all potential. And then as it moves back, I could draw a line like that, and it's going to get to here. The same point on the other side. Right? But as it moves through, what does it do? Here it's stopped. V equals 0. K equals 0. That's a turning point. But here, what's it doing? Here it's moving. Okay? So here it's like flying this way. Or if it came from there, it's flying that way. So here, and what's the U spring is 0. It's the maximum kinetic energy because it's the maximum velocity. So it's like it's just going back and forth through this potential energy diagram. It's really moving in 1D, but But if you think about this diagram, it's kind of like it's following the potential energy curve like that. And how high it is on the curve is how much potential energy it has. But what's this? This is the total mechanical energy right here. Is this line, right? Its total is its maximum potential here, its maximum here. We could draw the line all the way across. And then you could even pick a point and say, well, how does it break down here? Well, here you would say this bar is its kinetic, because this bar is its potential. Right? So this is how high it is in potential. I mean, it's not an area. I'm just trying to make it easier to see. It has this much potential, therefore it has to have this much kinetic. So when you're all the way over here, it's all kinetic, isn't it? Look at that. Just like we said, all kinetic. What about when you're right here? Oh, there's hardly any kinetic left. Right? There's just a little bit of kinetic and a lot of potential. So all it's doing is exchanging kinetic for potential as it bounces around back and forth in there. Okay? Moving around in a potential energy diagram. So it's really a plot of the potential, but you can think about both. You can think about potential and kinetic. Okay, now we want to get really weird. Okay, it's going to get messy on this diagram. You may not want to do this. I don't know if you can handle it. But what I'm going to do now is plot the kinetic energy on top of the potential energy diagram. It's okay. All right, so I'm going to start here, and it looks like this. It's like the upside down version. All right? So that way the sum of these two is always a constant. That's like what a parabola is or something. Okay? So when you're here, you're all kinetic. That's why the kinetic is all the way up to the energy line. When you're here, you're all potential. That's why the kinetic has made it to 0. Okay? So now you completely understand everything you could possibly do with that. And one thing I'll say about these diagrams is the way people physically think about them. Like, even though this represents a spring and a mass, and the only potential is a spring, the common way to think about them is as though this is a surface, and you're thinking about gravitational field near the Earth pulling things down. That's kind of the way to think about it, and it always, well, okay, in classical systems it always works. In quantum systems other things happen. But if you said, what would happen to a ball, if this were a ball in a bowl, what would it do? It would do exactly what the mass in the spring is doing. You'd have it up here, it's all gravitational potential, you'd release it, and it would flow down here, it'd be all kinetic here, gravitational potential is gone, and it would come up here and be all potential again. And it would just roll back and forth. Right? The ball would go back and forth just like the mass goes up and down. So when you're looking at one, when you want to intuit what's going to happen, just think of it as a solid surface and think of what gravity would do to a ball. And that's pretty much the right interpretation of it. Okay? Even if it's like a molecular bond or something. Let's see. So let's look at what we can do with this here.